So today we are going to discuss some more examples on group actions. The first one we are going to try is the group action on the collection of all left cosets of a group, of a subgroup in a group. So let H be a subgroup of a group G. It doesn't need to be an abelian group, and this doesn't need to be a normal subgroup, just a subgroup of a group. Let L be the collection of all left or right. We are going to try left only. Left cosets of H in G. Then L is a G set under the following action. So we are going to define an action from L, a group action of G on L, meaning we need to define a function from G cross L to L. And that definition is G times L is the collection of cosets of H in G. So it will be of the form XH, and that is equal to Gx of H. See, this X is in G, so Gx is in G. So this is a well-defined left coset. So this is how I am going to define the action. So this is a group and this is an element of the set. And this is again an element of the set. We need to prove that this is a well-defined action. Meaning, if XH is equal to YH, this is possible because X and Y's are representatives of that coset. If you take any two representatives, then we need to show that G operated on XH is equal to G operated on YH. Then only this definition goes well. If you take an example, let us take the symmetric group with element 3. So sigma 0, sigma 1, sigma 2, mu 1, mu 2 and mu 3. These are rotations and these are images. And one subgroup will be sigma 0, mu 1. So there will be 3 elements in the left coset. So L is H, sigma 1H and sigma 2H. See, in sigma 1H, you will have sigma 1 and mu 3. And sigma 2H, you will have sigma 2, mu 2. So what we need to show is, if you take any element, let us say sigma 2, that is our G, operated on, see this actually sigma 1H is equal to mu 3 of H, and this is equal to mu 2 of H, and H is equal to mu 1 of H. So we need to show that if you take any element, let us say um, mu2 of h, that should be equal to sigma 2 of h. Or probably we'll take a different one. This is 3 and this is 1. Makes a lot of sense. So sigma 1h and mu3 are equal. But if you operate like this, that also should give you the same result. And that's what we want to show. This is what we want to show. But xh is equal to xy. This means that y is equal to xh for some h in h. So that means, so if you take g of yh is equal to g of x h, because this is replaced by yh, and that is equal to gx of xh, and this is actually h is in h, so this is actually h, because if it's already in h, hh will be h only. So this is actually the identity map. So identity permutation. So xh, h. And that's what we want to show. So this is a well-defined action. But still we need to prove that all the axioms of the action are valid. So for example, the first one is E is the identity of G times any element in L should be mapped to xh, and that is clear because this is E times x is x, so this is clear. This is clear. Second one is G1 comma G2 belongs to G implies G1 of G2 xh is equal to G1 G2 of xh. That's also clear because all these G1 G2 and x are in G. So all the axioms of the actions are valid and it is a valid map. So L is a G set. And let us do another simple result. Let xi, where I is from an index set, be a collection of disjoint G sets for the same group G. Then the union of I from I xi is also a G set. Each of xi's are G sets and they are disjoint. Then their union is also a G set. So how do you show this? We need to define an action, G action on this. So define a G action, a group action on union of IXI by for X belongs to union, I belongs to IXI, X belongs to XI for some xi, for some I. Okay, then let G belongs to G, then Gx is equal to Gx in xi. So this is a well-defined action because this x is coming from a single xi, and each of these xi's are G sets. So the axioms of the G sets or the group actions follows automatically because they are all G sets. So since each xi's are G sets, this is a well defined action. See, if it is not disjoint, then this is not a valid, this need not be a valid definition. This x is coming from the union and this x is coming from a one single xi. That is why this is well defined. If it is coming, this x is coming from multiple xi's, this won't be a valid definition. As a corollary, of this result, we can arrive at the conclusion that every G set is a union of their orbits. See, Gx, let x be a G set, then Gx are, this is actually the orbit containing x, are orbits of x where x belongs to x. So you can write x is equal to union of x belongs to x, Gx is a union of disjoint orbits, and each orbit is a G set. So that means x is the union of all of its orbits. We don't need to prove like this because we already know that orbits are formed as a classes of an equivalence relation. But this is, I am taking this as a corollary of this result. That's all. Now let us do another simple result. Let x be a G set and y is a subset of x. Then define gy as g belongs to g such that gy is equal to y for all y in y. Then gy is a subgroup of G. This is coming from G, those elements of G that fixes Y. Okay, we know that if it fixes X, that is a subgroup. It's a normal subgroup. So, in order to prove that this is a subgroup, we need to show that this is closed, and we need to show that the identity belongs to this subset, and for every element there is an inverse. So let us take two elements from here. Let G1 comma G2 belongs to Gy, and that implies G1 y is equal to y and G2 y is equal to y for all y in y. And that means G1 G2 y is equal to G1 G2 y is y, and that is equal to y. And that implies G1 G2 belongs to G. Now since EY is equal to y, E belongs to Gy. And since Gy is equal to y, for G in Gy, y is equal to G inverse y implies G inverse also belongs to Gy. And that implies Gy is a subgroup of. Now let us do an example in geometry. Our group is R, the group of real numbers with addition. This is our group. You can say it is actually additive group of real numbers. Our set is R square. That is, there is no operation defined on this. This is just a plane. So any point in this plane belongs to X. So we need to define an action. So action is going to be from R cross to R square to R square. So in R square, in R we are going to assume that this is theta, any real number, and this is a point P, and that should go to another point. The way we are going to define is, let's take a point P, then you join that point to the origin, then any real number operating on this P will be another point with the same origin, another point it rotates this many angles, radians. Well, this doesn't need to be 2 pi. less than 2 pi, but you take theta mod 2 pi. So that many radians. So this is the action of, Q is the action of P on theta. So that is how we are defining the action. So let P be a point in R square and R be the additive group of real numbers. Then define a group action on R square by R times R square to R by the point P on R square is rotated along the line through the origin at an angle theta mod 2 pi, where theta belongs to R. So this is a well-defined action, but we still need to prove that the axioms are followed. So the identity of R is 0, meaning P is rotated through an angle 0 degrees. That means 0 times P is equal to P. The first part is done. So let theta 1 plus theta 2 or theta comma theta belongs to R. So theta 1 plus theta 2 of P is equal to theta 1 plus theta 2 plus theta theta 2p, because theta 1 plus theta 2, you can write it like this. First you rotate theta 2 angle, then you rotate theta 1 angle. So both the group action axioms are followed. So that means R square is a R set under this action. Now let us compute under this action the isotropy subgroup of any point other than the origin. So let P be a point on R square other than the origin. Then what is GP? Isotropic group containing the point P. Elements from R such that Rp is equal to P. And what is that? This P, this is the point P. So the value of R, the real number that retains the position of P when you rotate, that means 2 pi, 2 pi, 2 pi. So this is actually going to be the subgroup generated by 2 pi. And what is GP? This is actually the orbit containing P. And that means elements from R square such that X is related to, or you can say Q. Q is related to P. All the points in R square that are related to P. Related to P means there should be a theta in R such that theta Q is equal to P. Or you can say that is P is equal to theta Q for some theta in R. So what are they? See, let us take an element here, Q. You will not find any real number which when applied to on P will get this, because this radius is different. But if you have a same radius somewhere here, let us say Q dash, this is R and this is also R, then this is the action, this is the point after we get operated on P at this angle. So this is going to be the circle containing P with the center as origin. So we found the isotropy subgroup and orbit containing P. Now let us do one more result. Let X be a transitive G set and X0 belongs to X. It's any element in X. Then X is isomorphic to the collection of left cosets of Gx0. Well, we are already explained the isomorphism between two G sets of for the same group. So X is a set. In normal sense, you don't have an isomorphism from a set. But here X is a G set. So we already seen this isomorphism of sets earlier. If x and y are two G sets for same group G, then if there exists a map phi from x to y such that phi of gx is equal to g of phi x for all g in g and x in x, then x is isomorphic to y. This is a definition we used for comparing two G sets. Gx is actually from x, phi of gx is from y, x is from x, so phi of x is from y, so g of y is from y. So this is from y and this is also from y. But here x is given, x is a transitive G set. Y is the collection of all left cosets of gx0. gx0 is a subgroup of G. So we have already established another result before this, that the left coset, the collection of all left cosets of a subgroup of a group is a G set. So this makes sense now. So let us start showing this result. So gx0 is a subgroup of G. Let L be the collection of all left coset of gx0 in G. So what we need to prove, that we need to find out a map from x to L. So need to find a map psi from x to L that is a bijective map and satisfies the isomorphism rules. So what is that the definition of this function? So we need to take an element from x and map to a coset of gx0. So define psi as psi of x equal to gx0 where x equal to gx0. This is possible because x is transitive. Any two elements can be related like this. So x is an element of x, x is any other element from x. So they are connected through this y, through this g. And that g is the left coset you are defining to. Now, psi is well defined. How do you prove that it's well defined? If x is represented as g1x0 and g2x0, still it should point to the same left coset. So this is, so what we assume that x is equal to g1 x0, that is equal to g2 x0, and that implies g2 inverse g1 x0 is equal to x0, and that implies g2 inverse of g1 belongs to gx0, and that implies g2 belongs to g1 x0, and that implies g2 gx0 is equal to g1 gx0. So that implies psi is well defined. Now we don't need to write it that name. Now psi is 1 1. For that, we'll take two elements. Let x1 comma x2 belongs to x. That implies x1 is equal to g1 x0, x2 equal to g2 x0. So assume that psi of x1 is equal to psi of x2, and that implies g1 gx0 is equal to g2 gx0, because that is how we defined. So this implies g2 is equal to g1 g0 for some g0 belongs to gx0. Now let us start from here. x2 is equal to g2 x0. g2 is g1 g0 x0. g0 is from gx0, so this is actually x0, g1 x0, and that's equal to x1, and that implies psi is 1 1. Now we need to find out for every element in L there exists a x. So let G belongs to G and Gx0 belongs to L for any element in here. So so this actually, what does this mean? So let x prime belongs to gx0, and y is equal to gx prime. And that means, or you can say, you don't need to even write like this. You don't need to write this one. Don't need. So let x is equal to gx0, and that implies psi of x is equal to g. So we have, for every element in L, there is an element in X that is mapped to it. So it's 1 1 and on 2. But we still have to prove that, it remains to prove that psi of gx is equal to g psi of x for all g in g and x in x. So for this, we'll assume that let x equal to g1 x0. So gx equal to g1 x0. So psi of x equal to psi of gx equal to psi of gx equal to g1 gx0, and that is equal to g of g1 gx0, and that is equal to g of phi of x, because x is g1 x0. So this is phi of x. So we started off with sorry, not phi, this is psi. Psi of gx equal to g of psi x. So that means psi is a g set isomorphism between x and y. Now let us prove another result. Let x be a G set. It's not insisting that this is a transitive G set, it's just as G set. And x0 belongs to x. Then the cardinality of the orbit containing x0 is equal to the index of the isotropic group, subgroup x0 in G. And if G is finite, then the cardinality of Gx0 divides the cardinality of G. We are going to use some previous result to establish this. See, what is Gx0? Gx0 is the orbit containing x0, and that implies Gx0 is a transitive G set. Because every two elements in G0 are connected. Connected in the sense that one can be reached using the other from an action. So this is a transitive G set, and Gx0 is a subgroup of G, and that means Gx0, the orbit, is isomorphic to the left cossets of the collection of left cossets, the collection of left cossets of gx0 in G. And that means what? That means gx0, the cardinality of gx0 is equal to the cardinality of, or the number of, equal to the number of left cossets of gx0 in G, and that is nothing but the index of gx0. And when G is finite, G over gx0 is finite, and that implies gx0, the cardinality of divides because this divides G, and that is equal to gx0, the cardinality of gx0. So the cardinality of gx0 divides G.